All right, so welcome back. Today we're going to continue with functions, but we'll take a little bit different track with it. We'll start talking about error handling so that you can communicate between functions. When you call functions, you need to know that they successfully executed or not. And then we'll head a little bit into unit testing, because that's now that we've got functions and an actual testable unit, we can actually start to develop unit tests, and either in a informal framework as well as a formal framework next week. So just to motivate this topic, again, programs are always going to have potential for errors. Remember that we are online, so if you have any questions, you can go ahead and post to Piazza or to the video live stream here on YouTube. So we're going to have a potential for errors all the time, right? Some errors can be unexpected, right? So for example, somebody kicks out the cord, right? You can't really recover from that. You can't write software to plug something back in the wall. Somebody enters in a bad password, though. You can, re-prompt them for the password or something like that. And so some errors can be anticipated and protected against. Now, a lot of modern programming languages use what are called exception handling, and we'll talk about that here in a second, but C is not one of them. C uses what's called defensive programming. All right, so we can't, the approach here is that basically we can anticipate bad situations and handle those errors, right? That's why we call it error handling. What do you want to do in the event that one of those errors occurs? Right? We can predict that a user will mash the keyboard and give us some bad input or something like that. And when they do, what are we going to do about it? Some errors may be fatal errors, right? That we want the program to die in such an event. Right? There's really nothing that can be done to recover from that. You can detect the errors, but there's nothing that can be done. For example, instead of a bad password, suppose that you're trying to connect to a database system, and that database is down, or you have no internet connection or whatever, right? You can program a program to try again, and then try again, but at some point, unless you infinitely keep trying, you're going to have to say, all right, well, enough is enough. You need to fix something because I can't recover from this anymore. The program, that is, from the program's perspective. In C, our general strategy will be defensive programming, right? We're going to basically look before you leap, right? We're going to check for error conditions before we execute some dangerous or potentially dangerous code, right? I'll put potentially there, potentially dangerous code. Right? You're about to divide by 0, A divided by B. So you check the value of B. If it's 0, then you don't do it, right? You don't jump off that cliff. You look before you leap, right? And then in the event that you are about to do something wrong, then you do something else or you don't do it, right? So if you are about to perform some invalid or dangerous operation, then you don't do it, right? Instead, you communicate some sort of error back to the calling function. Right? So we want to be able to communicate that, look, I couldn't compute the quadratic roots because you gave me numbers that I can't deal with. I have no idea how to do imaginary numbers, so return with an error code. An error of type 1 happened. Or you have a different type of error, and so that you can communicate, well, this type of error happened, you can decide how to handle it one way. Or this different type of error happened, you can decide how to handle it a different way. Or everything was great, everything was hunky-dory, we don't need to worry about anything, there was no error at all. In general, that's going to be 0, right? Other programming languages, other modern programming languages, use full exception handling. And we're not going to talk too much about that, but I do want you to be aware of its existence. An exception handling is a different system where you don't look before you leap. You go ahead and do whatever you want. You go ahead and try that dangerous code. And if an exception happens, if you jump off that cliff, what we'll do is we'll catch that exception and we'll put you back up on the top of the cliff, and you can decide what to happen then, right? It's usually done with a try catch. That's why I'm using that terminology. You try this dangerous operation, you catch any exceptions, and you handle them potentially differently. There are things in the systems programming called traps and exceptions that are not necessarily the same thing as the modern programming exceptions here. So instead, we take a different track with C. We communicate the error, right? What we don't do, right? We don't quit, right? In other words, we don't use exit with some sort of error code in any function other than main, right? You've been doing this up to now because if you don't have the proper input in main, there's no way that you can continue, right? But you don't do this in any other function, right? Suppose that you did this. Suppose that the math library was like this. If you called square root on -1 and it suddenly quit out of your program, does that sound like a good design? Probably not. Instead, some sort of error code should be communicated back to the calling function that says, I can't handle imaginary roots, or I'll simply set your value to nan, not a number, right? And you can decide how to move on from that exception, that kind of error, right? If it did quit on you, then that's it. You can't do anything about it. You have no choice in the matter. You have no way to design around that. It's not flexible at all. So you do not quit. You do not exit in any function other than main. It is okay, right, to quit in main if you don't have the correct number of command line arguments, or the command line arguments are bad input, right, negative balance or something like that, like you did this last hack. It is okay to quit in main. It is not okay to quit anywhere else, right? You don't echo error messages, right? In other words, printf, i.e. printf, error, right? Some sort of error, because the vast majority of software is not written for humans. There is not somebody sitting there watching the computer screen of a program that's running 24/7, just waiting for it to print out an error message, and then they jump to and start dealing with it, right? We program so that we can recover from errors. In this event, we do something else. In this event, we do something else, right? We don't pollute the output with a bunch of error messages. Now, generally, you do sometimes do this, but you don't do it with printf. You do it with a full, sophisticated, what's called a logging system. And you can configure a logging system to log error messages, log information messages, warning messages. Somebody logged in, right? Somebody changed their password, so that you have a full listing of all of the system events that have occurred. But you do that in a proper logging system. For C, that's going to be, I think it's log4C is one library. There are dozens of these libraries that you can use. We're not going to get into it, but that's what you would properly do if you did want some sort of a logging system. That way you can redirect it to a file. You can redirect it and save it to a database. For high-level errors, you can shoot off. You can configure it to shoot off an automated email message to the system administrator, so that they can jump to and get on that rather than sitting there staring at the screen 24/7. So you do not echo error messages to the standard output. Instead, and then the things that we do is you don't do the dangerous operation. Instead, you return an integer error code indicating the type of error. Right. Generally, 0 is no error. Right? And we've seen that pattern before. 0 is what? Is it what value does 0 have in the context of true false? False. So ask yourself, was there an error? No, false. There was not an error. 0, right? Otherwise, was there an error of type 1? Was there an error of type 2? Was there an error of type 3, right? All 1, 2, 3, all those things are true, right? Was there an error? Yes, 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 right? All 3 of those things. So it follows that same kind of pattern, right? Also, you may want to avoid magic numbers. Right? And I'm going to go ahead and demonstrate what I mean by that by completing the task that we set out to complete on Monday. remember that we have this GetRoots function here that takes in coefficients of a quadratic equation, ax squared plus bx plus c, and then we compute the two roots. Remember that we said that by returning both of these roots as pass by pass by reference variables, that freed up the return value. Originally we had this as void. Then we changed it over to int so that we could actually detect errors. For example, a division by 0 error, or imaginary roots error, or null pointer errors. And then we ended up returning 1, 2, and 3, right? Now, would you have remembered what 1, 2, and 3 corresponded to if I had not just shown it to you? In fact, maybe you've got the memory of a goldfish. I'll just say I have a memory of the goldfish right now. What was 3? I don't remember. What was 4? What was 1? I don't remember. What was 2? I don't remember, right? So if I'm using these mysterious magic numbers, right, that have no inherent meaning whatsoever, then I'm going to get confused a lot, right? I don't know what those numbers meant. So in the event that I call GetRoots and I capture that error code, right, I can choose to handle those errors differently. If error code is equal to 1, okay, print an error message here to the user, printf, you must enter positive roots, I don't know, right? I forget what it was. So I have to scroll back up here and see, oh, okay, an error code of 1 means that they don't even have a quadratic equation. They have a linear equation. So I'll say that you must enter A cannot be 0, let's say. A cannot be 0. You have a linear function, right? In fact, we might choose to handle that error completely differently. You know how to solve roots of a linear equation, right? How? We've got bx is equal to bx plus c is equal to 0. So minus c onto the other side, divide by b. So minus c divide by b. That's going to be my root, right? So double solution, I'll say, is equal to, right? Yes, help me out on my basic algebra here, right? And then I'll go ahead and printf. Instead of printing an error message here, I'll just go ahead and handle it differently. I know how to solve linear equations, right? So you actually have a linear equation with solution. It's still considered a root, right? Percent f and the line, solution. There we go. So there I was not choosing to treat that as an error at all, right? Now that function thinks it's an error, but I know that this other situation happened that I can handle differently. That's why it's called error handling it, right? Now if they enter the other one, else if error code is equal to 2. Now again, I forget what that is. Anybody? Again, memory of the goldfish. Right? 2. Oh, okay. That's imaginary roots, right? So I'll have to pull in a library at this point and then do imaginary roots, et cetera, or I'll just say printf, I don't want to do that, right? I cannot, this program cannot handle imaginary complex roots, basically, complex roots. Right? Don't call them imaginary, right? Else if, and then what was the error of the error code? Something seriously went wrong here because we passed in null, right? So printf error null pointer, right? Call Bret Hart. I showed that to you, right? The Bret Hart video? Okay, all right. Else, maybe it's not that funny. I thought it was. All right. Otherwise, I'll go ahead. There is no error, so I'll go ahead and just print out the roots right here, okay? And that was only possible because I was getting the error code from the function, okay? Let's go ahead and GCC this and make sure that it works. I think I did everything correct. Oops. All right. LM, of course. Root 2. Oops, what did I do wrong? Root 1, root 2. Root 1, root 2. Oh, %f, no? On line 35. Oh, that's right. These are, I must have had it in a different condition that we left off on Monday. That should be all right there. All right. So call back to what we were doing last time. Why is that wrong? What is root 1? What kind of variable? Just a regular old double. What does putting an ampersand in front of a regular old variable give you? The memory address of that variable. And are you printing out the value stored in that variable, or are you printing out the memory address of that variable? This would be proper, but of course it would just print out some mysterious, weird memory address. Right? So I'm going to go ahead and take out that ampersand there because I actually want to print the roots. Okay? All right. There we go. And come down here, compile it, run it, a.out. Right. And we get the roots from before. What if I change it so that b is very small here, a would have to be large? We're going to get imaginary roots out of this thing probably. Right. There. Can't handle complex roots. And if I enter in 0 and something again large, then I should get that it's a linear equation with solution 1. Is that correct? That can't be right. 10x should be negative b divided by c. Oh, what's wrong? Tell me. They're integers. Integers divided by integers are integers. So double. There we go. You should go back and change these to doubles because integer coefficients on a quadratic equation, that's very, very limiting, right? But anyway, there we go. And we have a linear equation with that solution. Right? Let's solve this problem. These are called magic numbers. Where did you get that 1? Magic. Where did you get that 2? Where did you get that 3? Magic, magic, right? If you have magic numbers, in other words, meaningless numbers that are just assigned to an error of type 1, an error of type 2, an error of type 3, you're always having to go back and look what were those errors, right? In fact, in POSIX, in POSIX compliant systems, POSIX error, no. There are a couple of, not a couple hundred, but where are they? Okay, that's PHP. Should not have looked at that. Here we go. Maybe one of these others. There we go. Oh, that's it? Come on, I want a full error no. Error no.h. Not tutorials point. Maybe this one. Right. So in POSIX compliant systems, there are 130 some errors that are officially recognized, right? What if I said, okay, without looking at the documentation, what is error number 99, right? Are you going to know that off the top of your head? No. In fact, with our simple program here, come back to it a week from now, and I will guarantee you will forget what the order was of 1, 2, and 3, right? But that's all right, because what we can do is we can define aliases for these things. Instead of, well, this mysterious magic number, number 94, we can say sock no support, right? The socket type is not supported, right? So it's still kind of cryptic, but at least it's a human readable version of that error code. So how does POSIX C do this? Using, what are these things called again? Macros. Define pi to be 3.14159. So that when you compile this, the preprocessor goes in. Anytime that it sees this loop, too many symbolic links encountered, error, it will replace that with 40, right? So that it can actually, use this magic number at compile time. I'm going to show you a different solution. And for that, we need some new syntax here. Enumerated types. So what is an enumeration in plain old English? If I have an enumerated list, what is it?
You assign a number to each item.
Yeah, it's the first element, the second element. It's a list, right? It's an ordered list. The first element, the second element, that's the third element, etc. An enumeration is an ordered list of things, right? In C, you can define an enumerated type. Right? So I'm just going to go ahead and start by giving you a full example here. All right. I'm going to define a type. And so I use the syntax type def, which, what do you think that's short for? Type definition, exactly, right? And it's an enumerated type, so it also is abbreviated to enum, right? Then I have opening and closing curly brackets. I am defining a list, right? Let's go ahead and define the days of the week. So, what's the first day of the week?
Sunday.
Sunday, okay. Sunday. You know, there's always some debate about that. Sometimes Monday is the first day of the week, right? Sunday, because the weekend, Sunday's at the beginning, it's the weekend, right? Whatever, right? Don't get into arguments about like that, right? Monday, and then of course Tuesday. Right? And you'll note here, how am I, look at my casing conventions. What am I doing with everything?
All caps.
All caps. If it was multiple words, it would look something like this. Hello underscore world. This is known as upper underscore casing, right? But that's not a day of the week. As I'm writing these, do you know what the days of the week are named for? Nice piece of trivia. Say what? Sunday, of course, would be just sun, right? And then Monday would be moon. And then we get into the gods. Tyre's Day, right? Tyre, Roman god, I think. Wednesday, Odin's Day, Odin, Norse mythology. Thor's Day, also Thor from Norse. Freya, also Odin, I think, right? Is what? Oh, okay. And then Saturday is Saturn from Saturn. You know, the Titan, yeah, the Greek Titan or whatever, right? Anyway, our months have meanings too. If you don't know, October is the 8th month. Did you know that? Yeah, because July and August were added later on. We used to have 10 months, right? It used to be more decimal system oriented, right? Anyway, so why would you want to define something like this? Because you have a predefined list with specific elements that probably aren't going to change that much, right? Days of the week, months of the calendar year, right? Nobody's adding any months for 2,000 years at least, right? Nobody's added another month. We're not adding any more days anytime soon, right? So this is a list. Now, internally what happens is that C will actually treat these as numbers. Sunday will have a value of 0. Monday will have a value of 1. Tuesday, ... Saturday will have what value? Because we started at 0, remember? 6, right? Now, that last comma, or the Oxford comma, or whatever you want to call it, is optional. You can go ahead and put that in as well. But they are separated by commas. Now, white space doesn't matter, but doesn't that look like a nice enumerated list? First item, second item, third item. If you did it like this, it would be syntactically correct, but it's not as readable, right? So generally you want one to align. So, let's note the things about the style and the syntax here. We use type def enum to define an enumerated type. We provide a name for the type at the end and end it with a semicolon. Right? Style, use upper camel casing for the type name, right? And use upper underscore casing for the values, right? Each value has internally an integer value which starts at 0. So unfortunately in C, this is a very weak type in that you can get yourself into some trouble, right? So be careful. Because these are integers, you can treat them like integers. You don't want to do that though. For example, this is a proper way of doing it. Day of week, today, is equal to, today is Wednesday, Wednesday. Right. Wednesday. There we go. Right. That's a proper way of doing it. If you want to check for equality, if today is equal to Friday, then printf lab. Right. Right. You can check it for equality. You can reassign values. You can do whatever you want. Unfortunately, you can also do something like this. You can, but don't. Say Saturday, let's say today is equal to today plus 10. So what is today? Today is Wednesday. What is Wednesday plus 10? Next week? Time works like that, but the code does not work like that. Wednesday is 0, 1, 2, 3, and 3 plus 10 is 13. Do you see a 13th day here? Nope. So already we've gone out of scope, and it's not overflow or anything like that because of the way that C internally represents enumerated types. Arguably in a hackish way, it just assigns integer values and then treats it like an integer.
So that won't throw any kind of error, like
Nope.
if you exceed your enumerated list?
Nope, not at all. You can do something like this. You can go ahead and say mod out, and there are tricks like this. Mod out by 7, right, because that's the size of the list. In fact, there are hackish ways of, you always add a last element, and then that tells you how many other elements there are. So I could add another day in there after Saturday, number of days, right? That would automatically get the value 7. And then I don't have to hard code that 7. I could go number of days, right? That's really hackish though. Don't do that.
So why is this better than the macros?
It's not, okay, good question, right? So they went with macros, right? 6 of one, half a dozen of the other, right? But one, it gives me an opportunity to show you enumerated types, other than usage besides error codes. For example, you could do this with macros as well. But the other argument for using enumerated types instead of macros is because of debugging. Those macros will be gone after the preprocessor gets done with everything. And they're all erased. Now they're all just magic numbers again. If you were to run your program through a debugger, when we get to it, we'll cover GDB. But when you run it through a debugger, all you're going to see there is 45. And then you're going to have to go back to the documentation to see what the hell was 45. But if you used an enumerated type instead, then you will see Wednesday, right? And it's much easier to debug. So the argument, it's not a very compelling argument. It's just a slightly, like all things being equal, this one is a little bit better, right? So that's why.
Can you assign numbers arbitrarily?
Yes, you can, but I would not recommend it. For example, you could say that Sunday starts at 10, and then it'll go 11, 12, 13, 14, 15, right? Or you can go ahead and assign all of them 10, 20, 30, 40 if you really want to, but you're doing something weird for what purpose, right? I think you can even skip things. You can go 10, and then this one will be 30, right? So this would end up being 10, 11, 30, 31, et cetera, et cetera. What? Right? Again, the whole point of doing this is to get rid of those damn magic numbers, right? So you don't have to have all this guesswork of what did 5 stand for again, right? Okay. All right, but you should know and understand that they are internally just integers. So be careful and don't do weird stuff like that. All right. You can go Monday plus Tuesday. What is that? It doesn't end up being Wednesday, right? Monday plus Tuesday, 1 plus 2 ends up being 3, which ends up being 0, 1, 2, Wednesday. Oh, I guess it would be 1, 2, Wednesday. So 1 plus Wednesday is going to be, oh, that's just because I'm doing Monday. So 2 plus 5 is going to be, Friday. Some weird thing, right? Whatever.
Calendar math.
Yeah, exactly. Now, if you do want to do time math and stuff like that, then you bring in a library to do it. And you might have seen that in your first lab where we did birthday calculations, how many days, how old is this person, et cetera, et cetera. And if you're wanting to get in that, it is not at all portable. So one system might do it completely different than another system, but you can see how it works. There's a built-in structural type, which we'll get to later on in the time library, time.h. Right? Okay. So the other elements, of course, would be that the list is delimited by commas, and generally one item per line. Okay. All right. So let's go back and fix this, and let's not have these mysterious numbers anymore. Let's define an enumerated type for our types of errors. Now, to do that, I'm going to go ahead and modularize this code first of all. I'm going to go ahead and take that, that body, and I'm going to bring it over here to my utils library that I've been building. Remember that we had the harmonic series, the AGM function, and now we've got this GetRoots function. Don't forget to also put in your prototype. The order doesn't matter. The prototype is the signature followed by the semicolon. And what else do you do on prototypes? Documentation. Right? Computes the roots of a quadratic equation, right? Ax squared plus bx plus c equals 0, and places the results in the two pass by reference variables. Return, and then of course we also want to document the fact that we are returning an error code now. Returns an error code in the event of an error, C, and this is what we're going to do now. In my same .h file, I'm going to define that type def. Type def, enum. What should I call this if it's going to represent an error? Error? Okay. Now be careful because I am polluting the namespace here. So once I have one thing named error, that's the only thing that can be named error. What if I bring in library A because I really want to use that library, but it's already also defined something named error? And I bring in a third library because I want to use something in that library, and it's got something named error, right? It's already been polluted. The namespace, the names that I can use has been polluted already with that name error. Generally, what you want to be is a little bit more specific. What kind of error? I don't know, root errors? Root error? What? Yeah, root errors and utils. Right? Now there are ways around this that you can use. You can do include guards. You can do conditional compilation, stuff like that. But ultimately, if you have a compiled library and another compiled library and they have a conflict, you've got a real problem. Then you've got some ABI programming probably at that point, application binary interface, to say that I want you to compile with that thing over there, right? So we're not going to get into that though. Right? So what type of errors did we think about and program? All right, and there's a null pointer error. If you want to, you can follow the pattern that the POSIX-C has. They begin everything with an E, right? So that they're not polluting the namespace, right? If it begins with an E, then that's a POSIX error, and shame on you for beginning all of your errors with an E, right? That's its way of avoiding polluting the namespace. Right? I'll just go ahead and call it null pointer error. Right? I'll prepend all my stuff with the full word error. Right? What else? What was there? Division by 0 error. Right. Anything else?
The linear error.
That was the division by 0, right? And then null pointer, and then
Linear equation error. That's one where A is not equal.
yeah. So you would end up dividing blah 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 over 2a, right? So a is 0. You would end up dividing by 0, and the other one is complex root error. Right. Except that we also return 0 in the event of no error, right? By convention, remember? We end up returning 0 down here. So should I take care of that over here in my type def? This would end up being 0. As I have it right now, this would end up being 0. This would end up being 1, 2. So one thing I could do is no error. Right? Spell it right. There we go. There. Document that, right? These are the types of errors. Types of errors associated with GetRoots. Right? And then down here I could say see root error. Right? See what kind of errors those are. Now I don't have to guess anymore. I can use these over in the actual function. Right? So instead of returning 1, in fact it doesn't even correspond to 1 anymore, it's just a division by 0 error. Right? Human readable manner. Right? This one will be complex root error. And this one will be null pointer error. Right? And what about this one down here? No error. Okay? And I can reuse these over in my demo because I've included, once I do, I include the utils.h file. And that's why we put the enumerated type in the h file. Because if you're going to include the header file, you need to know about these errors in order to use them. So if the error code is equal to division by 0 error, right? I didn't even have to remember which one was which. In fact, it's not even in the same order anymore. This one is complex root error. Humans are good at reading English or native language, right? We're not good at reading numbers. Right? And this is null pointer error. And then, of course, I don't have to check for it because there is no error. Right? Let's go ahead and compile these things all together. Remember now, I've got utils.c, utils.h, and demo. How do I compile all of those things together? You're going to get more practice in this Friday in both your lab and hack. How do I do this again? I need to compile the utils.h, or .c, excuse me. That produces a utils.o file. O stands for object. Right? If I were to open that up, in fact, let's go ahead and try. It's probably not going to let me. Right? This file is not displayed in the editor because it is either binary or uses unsupported test. Do you want to open it? Oh, yes. Yes, I do. Oh, okay. Whoa, cool. There's a hex editor built in. Okay, I might be going down the rabbit hole here. It might be installing something in the background. All right, I can always do hex dump, I guess, of utils.o. Hex editors are great things. Why? You can if you've got a save game somewhere, right? What you can do is you can go in and hex edit it, and you can change. If you know exactly which bytes correspond to your score, you can give yourself a better score, right? That's how cheats work, right? Or that's how old school cheats work, at least. Right? All right, so nobody games. I don't game that much. Anyway, hex editors will allow you to, if you can reverse engineer a save game or something like that, you can do whatever you want, right? All right, so now that I've got that O, how do I compile the demo together? GCC, demo.c, utils.o, and because I'm using the math library, I need -lm. Oops, I must have spelled it wrong. But it's telling me that you probably meant division by 0. Did I? Which one did I? Division by 0? Error. Okay, there we go. Yep. Good GCC telling me and giving me a suggestion too on, did you actually mean this thing, right? And yes, I did. Right? Now when I do a.out, I get the same errors, but it made no difference to the end user, right? The end user is getting the same messages, but look at how much easier this code is to read, right? Division by 0 error. Okay, I know exactly what's going on right now. Complex root error, null pointer error, right? I know exactly what's going on because they're human readable descriptions of what's going on. Right? All right, fun. Now, let's start testing, more rigorously testing our stuff. This means that we're going to have to start talking about proper unit tests, okay? I don't have very many notes on this, but unit tests. I do have a video on it in the pre-prepared slides. So what is a unit test? Well, first of all, a unit is a piece of code, usually a function, but it could be a class, it could be a structure, it could be whatever. It could just be a snippet of code if you want, that can be tested. Right? A unit test is an input-output pair that is known to be correct. Right? We unit test by feeding the input into our unit, in other words, our function, right? And comparing the result to the known correct output. So how do we know them to be correct, and how do we know them to be incorrect? If it's a number, you pull out a calculator and you figure it out, right? Otherwise, you construct your unit test. Before you even look at your code, you come up with an input. I want to test this input. All right, well, what is my expectation? This is my expected output. Input, expected output. That allows you to feed this input into your function and look at its output. Do they match? Then we say that that unit test passes, right? If they match, that unit test passes. Right? If they do not match, that unit test fails. Right? A collection of unit tests is known as a test suite. Right? Suite. Right? Here's the picture of a single unit test. A unit test has to have two things, an input and an output. When we say output, of course, we can mean other things. It could be an actual return result. It could be several return results. For example, what we're going to unit test is the quadratic roots. We're going to get back actually 3 outputs. We're going to get the root 1, root 2, and the error code. We're going to want to check all 3 of those things because we want to make sure that it's functioning with respect to all 3 outputs. So it could be a tuple, right? Multiple things. It could be a result, right? The test could be, if I feed this into the database, then my expectation is that it gets saved to the database. And so the output is some sort of a verification, much more sophisticated than just an output. It's a, let's go into the database and find out, did it work? Did it actually save? Right? But in any case, you take this input and you feed it into your unit of code. That gives you this output, right? So you can take this output, and you ask, are they equal? Or sometimes you even ask, are they good enough? Are they close enough? And if so, then you pass. If not, you fail. Right? And you can automate this by writing these unit tests and rerunning them over and over and over again. It's great because if you come up with, if a future bug is reported, right? If a future bug is reported, then you have a new unit test to debug and test with, right? If somebody reports, hey, it didn't work when I gave it 0, right? Then, okay, well, let's go back to the drawing board on my design. If you feed it 0, what is my expected output? It's 5. All right, well, we didn't get that. We got 4. Oh, okay. Well, let's put this unit test into our testing framework so that we can run it as many times as we need to. Then we'll go ahead and go debug, and okay, here's the problem. Here's the bug. I'll fix that bug. Then you can go back to your unit tests and rerun them all, right? If a future change or fix, well, I'll just say that, not if, but a future change or fix that breaks other unit tests is known as a regression. Have you ever heard the term regression or regress? Regress back to the mean is usually what it means, right? So, you know, if a ball player is having a really, really great a month or something like that, then the expectation is that they will regress eventually back to the mean because nobody can perform at a high level consistently for the entire season, right? So at some point, you expect them to go back down. You expect them to regress to, what's the opposite of it? Improve? Unimprove, right? You expect them to do worse in the future because this is their average and they're performing above their average, right? And so that's a regression. They go back to what they were like, right? And this is a regression in that something that was passing before now fails. The only way that we know that is if we have this suite of tests that is automatable and we can run these 100 tests over and over again with the click of a button or the execution of a command, right? If we do this in an ad hoc manner, right, you'd have to go through and manually type all of these things, all 100 tests over and over and over again. One fails, back, redo it, rework it, fix it, now rerun all 100 tests manually again and again and again until everything passes. You don't want to do that. You want to automate this process. And so that's why we want automated unit testing, okay? The more tests you have, the higher certainty you have that your code is correct. Right? No amount of tests will ever guarantee that your code is 100% correct. That requires a mathematical proof, right? And now you are in the world of mathematics, and guess what? There's another world of mathematics called meta-mathematics that says that there are things that are not provable at all, right? So there are some programs that cannot be proven to be correct at all. In fact, there are proofs that show that there are no programs for certain problems. Certain problems are called what are called undecidable, right? Given a program and whether or not it gets caught in an infinite loop, deciding whether or not it gets caught in an infinite loop or it eventually terminates on any given input, that's an undecidable problem. Mathematically, you can show that there is no test that you can apply to prove one way or the other. Right? So, unit tests are a practical, empirical method of software testing. Right? And the more that you have, the more likely it is that it is correct. But also, you could test the same thing over and over and over again. You want to make sure that you have what's called good code coverage. Right? You want to test corner cases. You want to test edge cases, right? Extreme cases, etc. Right? You could have randomized tests. You could do, it's not called A/B testing, but I like to call it A/B test. I don't know, I don't have a good proper term for it, but it's how I grade all your stuff, right? You have a program, I have a program. Do these programs agree? If not, then, oh, maybe I made a bug, right? Not likely as this stuff has been served now for a couple of semesters, but it's always possible. The stuff, like many of you experienced this on Lab 3, there were no actual bugs in the grader. It's just that we were using tax rates from 2019, and the lab had been updated for 2021 or something like that. And so I never fixed it. Right? I never updated my program for the new tax rates or the tax brackets. We have program versus program, and if they agree, then there's a high expectation that they're both correct. If one disagrees and the other, if they disagree, one says one thing, one says another, then likely one of them is wrong, right? It has to be that one of them is wrong. But it is also possible that they're both wrong in exactly the same way and they agree on it, right? They get the wrong answer, both get the wrong answer, 4 instead of 5. Those are called false positives, false negatives, right? A false positive is when a test case is wrong, right? But the code is correct. You still know that something's wrong, right? And so you can go in and investigate. Is the test case actually right? Well, let me redo my calculations. No, the test case is right, so it's not a false positive. It's a positive. You have a bug in your program. You also have a false negative, right? There is a bug, but your tests do not indicate it. Right? In other words, your test agrees with the wrong thing. The program says 4, your test case says 4, but it's actually 5. Right? This is most likely because you didn't write your test case correctly. How do we write a test case correctly? You come up with the input, output, or the expected, I should say, expected input, output before you code. Right? This is called test-driven development. Now, it can be done in parallel, it can be done after, but the cardinal sin that you do not do is simply take an input, run it through your program, you get an output of 4, and you say, oh, well, the input must have been 4, or the expected output must have been 4, right? That's ex post facto testing. Don't do that, right? It said 4, it must be right. No, you need to come up with an independent way of verifying that your tests are correct. If that means I'm opening up Wolfram Alpha and just plugging in numbers and trusting Wolfram Alpha, then do it, right? When you get into your hacks, you'll be doing color utility functions, translating from RGB, red, blue, green values, over to CMYK, which is cyan, yellow, magenta, and then toner black. for printing. That's how printing color works, CMYK. Screens are RGB, right? They have red, green, and blue, and then they blend them together to create other colors. Translating between those two, you'll write a bunch of utility functions to do that. How can you create unit tests for that? Well, you do a Google search for an online calculator for RGB to CMYK, right? And you trust that that works, and you create a test case from it, right? Some other means, right? Now that other means might be wrong, in which case, again, you might end up having a false positive or a false negative or something like that, but at least you have some high certainty that it is correct. Again, there's no guarantee that your code is ever 100% correct, unless you've got a code, like what is it called? Oh yeah, it's a programming language called COQ, right? It's French for, what is it? Rooster, right? And so it is pronounced cock, yes, right? Programming language. There, complete guide. It is a functional programming language where you can actually prove things about its correctness. You can write coding proofs for the correctness of other code. Right? Now again, it is an incomplete kind of thing, but it is a niche language. It's a mathematical language, right? So there's another quote. I forget who it's by, but there are only two kinds of programming languages: the ones that everybody hates and the ones that nobody uses. So this falls under the second category. Nobody uses it. Academics probably use it. Right? All right. So let's write some test cases. I've got a utils tester right here. Right? Let's go ahead and take those inputs that we were working with before and figure out what they should be. So for example, let's go ahead and go with int a, b, and c. Right? And also create an integer to capture the error code. And let's set some expectations here. If I set a equal to 10, b equal to 20, and c equal to 30, let's go 10. Right? What are my expectations for the roots? So let's go ahead and create another variable. Double expected root a, expected root b. Let's set up a test case here. That's my input. What's my expected output? Anybody want to pull out their calculators? Or I'll just do it for you. What was it again? 10, 20, 10? All right, so 10x squared plus 20x plus 10 roots of. You'll understand that. Oh, cool. Nice, well-behaved root there, right there. What are my roots? -1, and -1. What does multiplicity mean? The number of times something appears. So both roots are -1. What's my expectation then? -1 and -1. And what's my expected error code?
0.
All right. And so I need to create that, of course.
Or do we say no error?
Yeah, expected error code. Good point. It should be no error. There we go. So there's my inputs. There's my expected outputs. And there's my actual error code. And I guess I need some double output root A and output root B. You can come up with better names. Actual output. I don't know. Does that match up better? Actual root A. Okay. No, because it's out. Oh, I'm testing it. It's not actual.
Calculated?
Calculated? Ah, it's too long. I want it to line it up right like that because I want it to look good. Right. Calculated? Right. Calced? All right, there's another quote that I'll share with you. I think I might have shared it before. There are only two difficult things in computer science: cache invalidation and naming things. So this is really, really difficult, right? A third thing that I'll share with you. Arguing about little minutia stuff like this is called bike shedding. Have you ever heard of that before? Right. So bike shedding is a term that you might eventually hear, especially in the business world and design and engineering and stuff like that. Bike shedding is where people argue about the inconsequential stuff because it's easy to do so. They do not argue about the important stuff because it is difficult to do so. And the term itself comes from, I think it's a thought experiment where they're designing a nuclear power plant, an extremely complex project, right? Nobody's arguing, the committee is sitting around, nobody's arguing about whether or not they're doing the proper mass or however these things are built, right? Nobody's arguing about the proper safety measures or redundancy or anything. What are they doing? They're arguing about what color the bike shed should be painted, right? Why? Because it takes a high level of understanding to even comprehend the complexity of a nuclear power plant. But any old idiot can just think that the blue is better than red, right? So you end up bike shedding about this kind of stuff. Forget about focus on the important stuff, right? Okay, so let's go ahead and test this now. My expected error code is there, so my actual error code will end up being a call to GetRoots, I think it was, right? A, B, and C. And the actual roots are calculated roots. And make sure to put an ampersand in front of those. Why? Because they are passed by reference variables. Right? And now I check all of those things. I can check them independently or I can check them all together. First of all, let's check for the error code. If the error code I get back is not equal to the expected error code, then I can issue an error message. Printf failed. Error code not as expected. Right? Expected %d got %d. You can be more formal in your language here if you want, but otherwise I'll just go ahead and go with expected error code, no error. And unfortunately, we're not going to get it to print out no error. It is going to end up printing 0. And then the actual error code that we get out, we would have to define a function that translates an error code to a human readable message if we wanted to print it out. Not too hard, but we're not to strings yet. And then it fails. So let's count up the number of failed, because I'm going to be doing this over and over and over again, right? So int num failed, or num passed, equals 0. Int num failed equals 0. And num failed will end up being ++. Okay? Else if the expected root A is not equal to the actual root A, the calculated root A, then I'll say that that also fails. First value is not as expected. Output will be equal to %d expected %f and the line. And so what is it? The output was this calculated, and the expected was expected root A, right? And I'll do a cut and paste for the second one. And you can see that this pattern is going to get kind of tedious. If I'm going to do this again, I will take this entire dozen or so lines of code, copy, paste, copy, paste, copy, paste. Right? Let's just go ahead and go through the motions, though, since we have time. The second value is not as expected, and that will be B and B. There we go. All right, num failed. Else, if nothing failed, what do? Num passed, ++. Do you want to know about that? There's no reason to print it out. Sometimes you might want to, just for your own edification, ooh, pass. Excellent, nice, right? But otherwise, in general, especially in the Unix world, no news is good news, right? So I would expect no news here. And I would expect a summary at the end that here's the number that you passed, here's the number that you failed, right? And that's it. Right? In fact, let's do that. Printf num passed is equal to %d and line num passed. Printf num failed %d and the line num failed. And then you can even do a percent, right? Percentage, line everything up nice and neat. Num passed divided by num passed plus num failed, making sure that you typecast at least one of those things. All right, excellent. Now let's see if it compiles. GCC, what is it, utils tester? Along with my utils, because that's what I'm testing. Probably want some math library in there. It works. There, num passed, num failed, 100%. So actually, instead of typecasting, let me go ahead and go with 100.0 times that so that it's on the correct scale. Oh, and here's a question. How do I get the percent sign? So I could say 100%.
Is it \?
You need to escape it. Good. I think that there's another way. We'll try it here. Nope. All right. It's one or the other. Do you see what I just did? Percent gives you percent. Why is it not backslashed escape, right? Okay, great. There's our one test case. 40 lines of code to get one test case working. But it's automatable. I can go back and make changes. I can run this, recompile it, and run it again. If I made the upfront investment of writing 100 test cases, then I have pretty damn good assurance that this is a good, that this is a well-tested software, right? And if I go back and refactor something, if I fix a bug, I don't have to go through that process again. I've got a test suite that I can run as many times as I want. If you want to add a new test case, go ahead. Give me another number.
7.
7. Oh, okay, 7. Give me your favorite small number. 3. All right. All right. So what's the expected? 7, 20, and 3. That's good enough. 7, 20, and 3. What's that?
Terrible to look at.
Terrible to look at. Exactly. All right, so there's the number. I'm not going to be able to represent that. So let's go ahead and take, in fact, let's go ahead and take this part and put it over here. The expected root one is there. The other one is this thing right here. I don't care about how many sig figs there are. There we go. And there should also be no error because those are both real roots, right? But otherwise, did I need to change anything else? What's that screaming out to you to do? Don't cut and paste. Don't cut paste. Do what? Put it into a function, a testing function of some sort.
Well, we do have to.
You'll take a hell of a lot more inputs. You'll take ABC, all right? You will take expected root 1, expected root 2, expected error code,
That,
right?
But you'll have to truncate your return, won't you?
Oh, well, okay, that's what I'm working towards.
Oh, okay.
You're jumping ahead. Don't do that. No, it's okay. It failed. Why did it fail? Tell us.
Oh, you have to truncate your return.
Yeah, I mean, what's going on here?
They're rounding to different precision.
Yeah, okay. Well, there's something else going on here. Those are in fact the roots, right? I just wrote them in the wrong order, but I'll show you that it still fails. There we go. There. It's giving me a message that says negative 0.158829, and I expected 0.158820. Right? So some tests, especially with floating point numbers, you have to build in a tolerance. Right? And we did this before when we actually implemented the AGM. Do you remember that? Well, we converged on the arithmetic geometric mean. When we got close enough, when we got to within 1 millionth, we said, good enough. So here's the fourth saying of the day. What's better than good?
Good enough.
Good enough, exactly. Why is it good enough? Because I think it's Machiavelli said that, or no, who was it? Whoever wrote Machiavelli. I forget now. Anyway, he said that perfect is the enemy of good, right? That's why we like something to be good enough, right? So I'm going to go ahead and put this into a macro, define tolerance to be this thing, right? And if these, now I'm not going to use this equals or not equals anymore. Instead, if it's close enough, if it's within that tolerance, I'm going to stop. How did we do that in the AGM? We took a difference, took the absolute value, fabs, because they are floating point numbers, and if it's less than that tolerance, then we say that it passes. Right? I am going to put that into a function. Int is close, or is close enough, right? Is close. Double A and double B. And let's document this. Returns true if A and B are within a tolerance of each other. False otherwise. So what does that function look like? I could put this into another utility class or some sort if you want to, but I'm just going to put it here for now. Right? If A minus B, the difference, and make sure that you take the absolute value because it could be negative, fabs. Right? If the difference is less than tolerance, or you could say less than equal to, if you're tolerating the tolerance, right, then you could say less than or equal to, then I'll return true. Remember, anything non-zero is true, so in this case, just 1. Right? Or, I think I brought in the std bool library. I could return, what is it? True, or is it true? Okay. Else, return false. Right. There we go. And it's still going to return an integer. You could change this to, I think, bool, right? If you want to, because you're bringing in that library. I'll just keep it like this, though. Okay. By the way, now that we understand enumerated types, guess what a bool is? It's just an enumerated type, 0 and 1. It might also be a macro, who knows, right? But the type itself is probably an enumerated type.
Does it do anything to actually save space?
Not really.
No.
And it's 2022. Who cares about 1 byte or something? Even in your embedded systems right now, right?
Yeah.
If you have an embedded system, I mean, if you're actually doing a breadboard or something, then your zeros and ones matter. But if you can buy an off-the-shelf Arduino and it's as powerful as all the 1960s computers combined, right?
Fair enough.
All right, so is close. I will change my code now up here. You can go ahead and change the other one on your own. If is close, if they're not close, then it fails. Right? So if they are not close, it fails. If they are close, then it passes. Else if these are not close, then it fails. And, oh, darn it, I didn't mean to do that with my, all right. I did not mean to do that with the error codes. Should you build in a tolerance for integers? Maybe, maybe not. I think our tests do, because when you translate from RGB to CMYK and then back, it could be off by 1 because that's how the mathematics works out. Right? So we do build in a tolerance there, but otherwise, it's really only for floating point numbers here. B and B. Right? And I'll kick that tolerance down so that it actually, like what is that? 10,000? Fine. Oh, no semicolon. What now? Is close, double A, double B. Oh. There we go. And now everything should pass. Yay. I'm back to up to 100%. Right. Lots of boilerplate here, right? Is close. You want to do another one. You want to test error conditions, right? You'll want to test other values. You'll want to test negative values. Cut, paste, cut, paste, cut, paste, cut, paste. That's what you'll be doing this Friday. We give you a framework. This is called an informal framework because it's me and eventually you writing all that code. What if we brought in a library to do all the heavy lifting for us, all the boilerplate for us? Right? And that's what you'll be doing not this Friday, but the Friday after that, where you bring in a library called CMaka. C, of course, for C programming language. And Maka is just mocking is where you're not making fun of the data, but you're mocking up data It's like a mock-up. You've probably heard of that, like a prototype or a mock-up, right? Where it's not a real thing. You just want to see how it looks, right? So you build something out of cardboard or something before you actually manufacture it. That's a mock-up to see what it looks like, right? That's what mocking of data is. It's faked data, created data, or created inputs and outputs in order to try to break your code. Right? And CMOCA is a library that you can use that takes care of all of this boilerplate kind of stuff. All you have to do is define inputs, outputs, and run that test over there. Right? Here's my expectation. That adds them all up and gives you a nice report at the end of percentage. So, questions? No? All right. Well then, have a good weekend, or have a good lab and hack session this Friday, and then have a good weekend after that.